5.2 Hess's Law. So Hess's Law states here, in a chemical reaction, the total change in chemical potential energy, enthalpy change, must be equal to the energy lost or gained by the reaction system. So that's a bit complicated. This is a little bit easier. So I've written this diagram up here. So this is sort of an ingenious sort of thing where algebra is actually applied to the real world. And so if you can get from A to B by going through A to C and then C to D and then D to B, then you're going to get the exact same result. You're going to get B coming out of this. So it has to be the exact same chemicals in the exact same stoichiometric ratios. Then you'll find that this delta H here is equal to these delta H1, 2, and 3. Now that's why it's really important this unit to know your definition, so that when you're given a delta H, you might be given a delta H of combustion or formation, which is coming up very soon in the next videos. You have to know what those delta H's are in order to make sure you get from A to B with nothing left over. And so this is really cool because it means that you can now mathematically know what the heat of reaction is going to be without ever doing the experiment. Or there could be reactions that are too dangerous to do, and you can do it mathematically and know what's going to happen. So here we have a problem. So this is an example. Let's say that you don't have the resources to do this for some reason, and so you know these two reactions here, and you're trying to work out what this one is. So what you first do is you can simply just add them together and get the answer if they are going to add up to give you that. Now for this one here, if you have a careful look, the CO's are on the same side. They have to be opposite in order if they're going to cancel out. Now we want C on the left, and this one's not on the left, so we're going to have to reverse this one. We want O on the left. Again, that needs to be reversed. That one's okay. And we want carbon on the right, so that one's not okay. CO2. So we want carbon on the left, so that's not okay. CO2 on the right, and that one is. So that one's definitely okay. So what we're going to do is first we rewrite it. So I've done that here. So this reaction here, you just reverse the symbol. Make sure you rewrite it so your setting out is good. And you can see the carbon's gone to here, the half O2's and the CO2's gone to there. Now what you need to do, this is actually going to add up, but if that still doesn't add up, you may need to times one of these by 2 or times one of them by 3. That's probably your next step. In this particular example, we don't need to do any timesing out because they add up quite nicely. So if you add them up, you'll see here that let's cross out the top one if I can find my pen. So what we have is we've redrawn everything. We've drawn both of these down here, and then we can cancel out those ones there, and the two halves add up to 1. That's where that came from. And so there's your final reaction. So we just write that out over here, and you've got minus 393.5 kilojoules per mole.